Let's take a look at the translational equilibrium of our little chunk of material. And in the process, what we will get are the governing equations that we'll be solving in the bike crank case, as well as the bolted flange. So I turn to Newton's second law, F equal to ma. And my little chunk is, I'm looking at it in the deformed state, so it's at rest, which means that there's no acceleration. So I can knock off this term. And I'm trained in fluid dynamics where you can almost never knock off that term, and it gives you a lot of headache because it's a nonlinear term, as we will see in the big ideas in fluid dynamics. So it's kind of fun to kind of knock that off. This means that what we have to do is to just sum the forces on our little chunk of material and set that to 0. And this is called a free body diagram for, drawing a free body diagram for those of you who have seen that idea before. It's kind of a very fundamental idea in statics. And if I look at force balance in the x direction, so I'm doing this balance in the x direction, and I'm doing a two-dimensional view because it's easier to understand. So I have the normal stress. So I have sigma x and sigma x here. And from here to here, sigma x is changed by a little amount, which I'm calling delta sigma x. And then the shear, I have tau xy, which since that's equal to tau yx, so I've just denoted as tau xy. So I have tau xy here, and again, this, the value here is a little bit different than the value here. And in the two-dimensional view, all forces in the, all the stresses in the z direction, we can set to 0. So these are the only two forces that come. And I can write a Taylor series expansion for the value here in terms of the value here. So I get the value here is the value here plus the rate of change in the x direction, that's this, times delta x being this distance here, plus higher order terms. And, we are looking at the limit as delta x tends to 0, so we can knock off the higher order terms. And that's, that's why we need to look in the limit as delta x tends to 0. Similarly, delta tau xy, I can write it in terms of a Taylor series expansion. And now I need the rate of change in the y direction. Okay, so I get the rate of change in the y direction. And there's a mistake here. This should be delta y plus higher order terms. And so now I can write my force balance in the x direction, and this is what I'll get. So first, let's take a look at the, this term that comes from the normal stresses. So the only thing remaining is that when you balance, this balances that. But that's given by this term. And I have to multiply the stress by the area. The area is delta y times delta z. So that gives me the area. And similarly for the net shear. And I've also put in a body force here. This could be like gravity. So if I was considering, let's say there was gravity in the x direction, you will have, rho g x, the component of gravity in the x direction times the volume. That'll give me the body force, and the body force is known, and it's proportional to the volume, and the force balance says that should be set to 0. Delta x, delta y, delta z, this term here is common throughout, and it's the volume of the element. So I can divide that through, and I'll get my final equation. So I get the rate of change of sigma x in the x direction plus, so there's a mistake here. This should be y plus, sorry about that. But, make those corrections, note those corrections, plus fx is equal to 0. So that's force balance per unit volume in the x direction. Similarly, one can write force balance in the y direction. And one can extend these ideas to 3D, and you'll get what are called the 3D differential equations of equilibrium. And so there we have to go to the full three-dimensional view of the stresses. In the x direction, we will get this equation. So in the 2D view, we had that term, that term, that term, and now we have to consider the contribution due to this shear, which is this stress over here. Similarly, in the y direction and the z direction, balance, force balance, and you get 3 equations and 6 unknown functions. And so one needs to bring in the additional equations, and that we'll do through Hooke's law. And these are called the governing equations for 3D elasticity, and these are the governing equations that ANSYS solves in, when we do the bike crank and the bolted flange. So let's take a look at the Hooke's law next.